We seem to be live, I believe. So, I hope all of you are ready for a post-mortem of our discussion last week. So, I hope everybody's staying safe. I know there are portions of the country that are very cold, some without power. Ahmed Mahdi, good to see you, buddy. Thanks for joining us. And for those international, I know we have some international people who dial into this, but I believe this is New Year's, isn't it? I can't remember year of the. I think it's year of the ox. Is that right? James Smith, pop that clutch, brother. Gustavo, hello. Good to see you online. We're filtering in. Yes, I think we are in the year of the ox, and I think today is New Year's. So Happy New Year. And we got Lou Grayhor in the house. Thanks, Lou. And you know what, Lou, you probably are going to be good for our discussion because I am going to be talking about application of overcurrent protective devices, circuit breakers, and you know all about those. And we're going to talk X to R ratio. Last time I checked, I thought I knew what the X to R ratio was we tested with, but you can keep me honest because that's the voodoo you do very well. Looks like I got a good stream health, and we are going to have a decent program today to just take a look at what we did last week. And if you remember, last week we had a great discussion we did a calculation on short circuit currents. So this was our screen last week. Live working tutorial, manual calculation of fault currents. And hey, we got Don Ganir. Hey, Don, we should have a good discussion today because we're going to talk. What my goal is today, last Thursday was a lot of math. We did complex variables. We were doing a lot of calculations, and I've had some dialogue since that program. On a few items. 5 screen Steve is ready. Awesome, Steve, roaming in the house. So I had some dialogue with people, and they were, pointing out, again, I had not prepared. I didn't do the calculation ahead of time, probably should have. But we came pretty doggone close. We made a couple mistakes in the process. I told you, I have a hard time with two things. When you're working to the right of the decimal point, I like working to the left of the decimal point. No doubts about it. I love those whole numbers, and the bigger the number that is, especially when it comes to payday. But, sometimes I work on the other side of that decimal point. And when you get a lot of numbers in there, if you're dealing with a 0.0000 or a 0.00000, you're going to lose a zero here and there. So the challenge is, especially if you're taking your PE exam, you're not going to have the benefit of having a YouTube group out there saying, hey, Tom, you forgot the zero. The other one I always have an issue with, always did in college, it was like a chore for me. It was a square root of 3. I'd go to a party, square root of 3 would stay home. Or square root of 3 would go to the party and I'd stay home. And I'd always leave that out in one way, shape, or form. So even in some of my math, when you're looking at me doing some equations, you're going to say, why does he put the square root of 3 in there when you can do some previous simplifications? But I do that because I got issues with square root of 3. So anyway, what we did last week, this was our one-line diagram. And what I want to do as well, I want to spend some time in our session today to talk about the conductors that I picked, why I picked what I picked, the transformer impedances, the X to R ratios of transformers, where you can get that information, why I picked 0.15 per unit on the motor, and probably what I should have picked for that motor. We'll talk about motor contribution, lumping, the assumptions that we'll make. Also, and what spurred this was James, I believe it was James Smith, was asking about that infinite bus calculation. We're going to take a look at this one-line diagram, and we're going to run the numbers, because now remember, I have it in SKM. I'm going to quickly run the numbers, and we can do it by hand as well, because I got all the per unit values. And we're going to take a look at an infinite bus. Take the utility out of the picture. Because there are some jurisdictions. Remember, there's a National Electrical Code requirement. SCCR, interrupting ratings of overcurrent protective devices, short circuit current ratings of equipment. From a manufacturer, we want to make sure our products are applied correctly. So we want to make sure that everybody's doing the due diligence on comparing. Because the last thing I need to do is to be pulled into a court case because our breaker achieved, or our fuse or our equipment achieved an unintended rapid disassembly in the field, as Dan Neeser would say, an unintentional rapid disassembly in the field, and we find out that it's because they were overdutied. So, meaning they were trying to stop the flow of current or hold it together under the pressures of current beyond which they were listed for. So, we're going to talk a little bit about what happens is the NEC has marking requirements, and over the last 2 code cycles, we're seeing more of this because people are missing comparing the available fault current with either the interrupting rating of the overcurrent device or the short circuit current rating of equipment. So the National Electrical Code has said, look, we know you need to make sure that the SCCR rating is greater than the available fault current, but we're going to make you mark the available fault current on the equipment. Hey, Felix, thanks for joining us. Felix, you got a package coming, buddy. It's going to be there. I don't know when, but I'm going to tell you what. That's the most expensive cup I have ever purchased. So I hope you enjoy it, and I hope it gets there in one piece all the ways down to Colombia. It shipped yesterday. I'll send you the tracking information. So what we do in the National Electrical Code is we now have marking requirements for available fault current. Well, there are some jurisdictions, some states actually, that take exception and say we don't want to have to mark the available fault current on equipment. And their logic is because the utility will change their available fault current, and it could change throughout the day, right? Because of switching and whatnot on the system side. So I want to show you where at least in a lot of cases that argument is bogus. Okay. And I'm going to run some numbers with you. I'm going to help you understand my perspective on that, which is based upon the math. It's based upon engineering. It's based upon what we did last Thursday. And we got Nihad El Sharif. Let me know, brother. Are you back in Canada or are you still in Egypt? I got your cup here. I was going to ship it, and I was right when you left. I'm not sure when you're coming back, so let me know if you are back in Canada. You've got your Shark Week cup that I have not shipped, and I owed that to 5 lucky people last year. And so, Mr. Procrastination, true form. No, I have no excuses. All right. So this was our one-line diagram last week. We looked at available fault current from a utility 125,000 amps with an X to R ratio of 8 all the way down through. So, Martian sounds pretty smart. I don't get it, Mr. Rock. I don't get that one. So what we did in our process, remember, we used per unit method of calculating fault currents. We also, which you don't realize, but we'll cover this in later power systems engineering topics that I bring to the table. And I'm going to use this one-line diagram. We're going to build on this diagram moving forward. So our goal last Thursday was to help you understand how a short circuit study is done and on a simple system, relatively simple. I mean, we did have a motor, which adds a little complexity. Whether it's a utility or a generator, it's just what the impedance value is, and we'll talk about that as well. But you have an understanding of what's going on. So the larger the system gets, the larger that the impedance diagram will get. But the first step is to establish the per unit base values. And that's what we did. Remember, we have 3 zones. We've got the 4160 side of that transformer. We've got the 480 volt side of this transformer, and we have the 208 volt side of that downstream transformer. And for each of those zones, we calculated base values. one of the questions that I had, hey, Matarabasi, good to see you. It's snowing again. Jeez, oh man, don't shovel, Mathur. What you got to do is get a snowblower, brother. You know, it's new technology these years. You know, I think they just came out with them. You stand behind them, and then you press this thing, and it just blows the snow for you. I'm just saying. Anyway, now the question I had that came in, I'm calling the 4160 V base, and the gentleman, two people had. One person sent me an email, one person commented and said, why do you keep calling 480 volt, which is the actual voltage, the base voltage? And the reason I'm doing it, I'm taking you down the road of a per unit system. Now, if you think about what we're showing here, V base is 480. I'm establishing that as my base voltage. What's my per unit voltage? Remember what per unit is. Per unit, and I had to go out and buy more pens yesterday. Went out in the snow, in the bustling snow. Remember, voltage per unit is equal to actual over base. So when we were doing our impedance diagram and we were calculating fault currents, remember, we put that entire circuit into what we call a Thevenin equivalent. What is a Thevenin equivalent? A Thevenin equivalent is a voltage in series with an impedance. So what we did was we took this one line diagram and we created an impedance diagram. Right. So the first thing we did was we said we're going to create an impedance diagram. So we had to identify all of the major aspects of impedance. And then we converted every one of these components into a real and a reactive component, an R plus a JX. And then we converted that to polar, which we'll talk about some complex variable stuff again. I want to help you understand a little bit what's going on there as well. But in any case, if we want to calculate the available fault current at bus A, I create what I call a Thevenin equivalent looking back to the utility. So what you would do is you're taking that one line diagram that looks like this, a bunch of impedances down to a bus A, and we'll throw the motor in there for giggles, right? And this was the utility, this was C1, this was T1, and this was C2, conductor 2. What we did was we turned this into a Thevenin equivalent looking back from bus A. And what do we have? We have 1, 2, 3, 4 in parallel with the motor. So this was utility, C1, T1, C2. So, and this was voltage. Now, since we're in per unit, voltage per unit, and I'm calculating where is bus A? Bus A was right there, which is the one line diagram, 480 volts. So my voltage per unit at bus A is actual over base, 480 over 480. My voltage per unit is 1. So this was 1 at an angle of 0 voltage. So when I did my math, I did my equivalent, we'll call that Z equivalent. I short circuit was equal to 1 at an angle of 0 over Z equivalent. And then I multiplied that by the base current value, which is 1804 at bus A. So the reason, and some people are a lot more, I don't know what you would call it, a little bit looser or lackadaisical about crossing all their T's and I's. whenever I do, especially if you're taking the PE exam, what I do is I isolate my one line diagram into those zones. I put my kVA base in each. I put my voltage base in each, and I'll calculate my per unit values, my Z base and I base, and then I use that to make sure I calculate the right per unit values. I mean, on any type of exam or even in the real world, we never have a system that's all at one voltage. We've always got transformers in there. So that's why I did what I did, and I called V base as it is. It's V base. 4160 is V base. Actual is 4160. Per unit voltage is 1. I base is 208.18, and I use I base to calculate take my calculated per unit short circuit current multiplied by the I base, and I get my actual short circuit current. So that's sort of why I did that, to answer that question. And I sort of wrote down what I wanted to cover. So I wanted to cover the per unit, which is what I did there, to help you understand why I picked those numbers. And it is really important that you get these numbers right. Because just think about it. If you don't calculate the right base, you could do everything else right, and you screwed it up, right? It's that one last multiplication. And if you didn't get I base, that means you didn't get Z base right. So when you put all of your impedances in a per unit value, they're all wrong. So that's why it's really important to understand these base values. If you're going to do anything by hand, take an exam, for example, or if you're out in the field and you want to run a really quick calculation, it's really not hard. If you got one of these, and one of these is on your phone. So I have the HP calculator app on my phone. So we took this, we took all of that, we created we identified all of your impedances. Now, the utility X to R ratio and the utility available fault current. There is, we have a really good industry reference. It's called, in our consulting application guide, got a good reference for you with regard to power systems. And in this document, I'm scrolling up on it because I'm looking for the exact text. Here we go. So in this document, we try to get this so you can see it. And you know what's funny is I'm like I can see pictures in my head, and then a lot of times I know what's in a book. I know what it looks like on the page, but I just don't know the page number. So I know what this table looks like. I just don't know the table number. All right. So there's my, when you're in the design phase, you're not going to know the utility available fault current. You can make some guesses. If you're going to get, like say from their secondary network, you know, this sort of X to R ratio, you can take a guesstimate on what your available fault current is going to be. I don't know. And it depends on what you're doing. If you're worried about interrupting ratings and short circuit current ratings, the higher the better. If you're worried about incident energy, it's the lower the better, right? Because the lower lower fault currents will produce lower arcing currents, which will give you longer clearing times. They could give you longer clearing times. So I always, you know, you can use these. I usually use an X to R ratio of 8. I don't know if that's right or not, but I'll tell you what, if you vary the X to R ratio, and we can do that in SKM, you don't see much difference in your available fault current. Remember, we're power systems engineering. When you're in the field, you're trying to get in the ballpark, and if you're picking the interrupting rating of a circuit breaker at 22,000 amps when you've calculated 21,998 amps, you screwed up, right? You need to go to the next higher. Give yourself some breathing room. Don't try to cut things that close. I know we're not including a lot of impedances in the bus. You know, we talked about this last Thursday. We don't model the impedance of the of the bus inside of the or certain aspects of your power distribution system. So you're going to be at a little bit of an inflated number anyway. So, and it's all an estimate. So it's calculations. We got Ryan Jackson in the house. Ryan, good to see you. Cheers, brother. We got Nihad El Sharif still in Cairo, and I still have not gotten a picture, a selfie of adjective psychology related to or denoting mental images. I'm getting some mental images. Etiquette. All right there, Brian. Thanks for joining us, brother. Too high off screen. All right, I can't show in snowing in Connecticut. So we got some snow out there, all that good stuff. Thanks for joining in. Please use the chat message. You know, we can converse and go back and forth together. So anyway, you know, you can run some numbers. Again, go at the high end. If you're not sure what the available fault current is going to be from your utility, especially if you're on a secondary network, and you're going to model your transformer and then their secondary network, sort of like what we did in our one-line diagram, then I would say, you know, you'll want to model a higher number. I would not get into estimating incident energy until you get a little bit closer through your design. If you're trying to do some safety by design practices, there are some tools you can use, and we'll talk about that once we move into the arc flash analysis portion of our little adventure here with power systems engineering. But in any case, you know, these are some of the typical X to R ratios that we see in the systems. So, and our if you go to eaton.com, I'll put a link out here somewhere. Go up to eaton.com, go to the consulting. If you just search consulting application guide, Eaton, you'll find it. All right. So we did that. So the utility available fault current, and I show you, I've got an X to R ratio of 8, and it, you know, depends on this power distribution system. Now, the conductors. What I did in SKM for conductor 1, if you recall, and what I do, I don't know where my code book is. There it is. I went to this book, and I went to table 9. Now, remember, our exercise last week was not for you to follow where I'm getting all my numbers. My goal last week was to help you understand the math, help you understand the per unit system, complex variables, what's going on in the background, the details of the impedance values for every single component on every project. You're going to have to come up with where you're going to get your data. So I used what was in table 9 for alternating current, resistance, and reactance for 600 volt cables. Conductor 1 is at 4160. I know that. I knew that. I wasn't going to get into the details of going through finding the medium voltage because really I didn't have the time, and I wasn't going to start to, I didn't have the time to go down the road to say, here's where I'm going to get my medium voltage conductors. Now, if you go into SKM and you pick a medium voltage conductor, they're going to have data there. They're going to have an impedance and a resistance value. I don't know where they got that information. If depending upon the project that I'm working on, if it's a commercial job, and I just want to get in the ballpark, and I know I'm going to be my interrupting ratings aren't going to be anywhere near where I get my fault current values. I'm just going to get into the ballpark. I'm going to run my analysis. I'm not going to die on that hill trying to find out what are the exact impedance values of the conductors that I've got installed. If I am in a life safety system, if I'm in a critical system where I think it might matter, I'm probably going to figure out what conductors I'm going to use. I'm going to contact Okanite, Southwire, whatever manufacturer, and I'm sure their websites have impedance values for their specific conductors. I can enter them. What I showed you on SKM is how I overrode the library and just put my numbers in. So it didn't matter what voltage conductor I picked because I was using SKM to do the math for me. And I wanted to use the exact impedance numbers. And I just went from the book, from chapter 9, but be mindful, chapter 9 impedances are only for 600 volts conductors. There is nothing in here that I can find that talks about medium voltage conductors. Now, I don't know why that is. I don't know if we just don't care about medium voltage conductors. I don't know if it's because not too many people do voltage drop studies on medium voltage conductors, but we just don't have an ohms per 1,000 feet for medium voltage conductors. So if you're out there, then take a look and tell me what you use for your impedances on your conductors. Do you just grab what's in the software, or do you do something different? But if you pick the right library in, and here I'll show you. If I come over here to my SKM and I double click on cable 1, I'm not going to change it, but if I go to library, you'll notice that I've got high voltage and low voltage. So if I go out of the high voltage, and medium voltage group, I'll get the right conductors. In fact, I did change it, but I went in and I changed the impedance values back. So I selected the right voltage rating, but I went back and changed the impedance values anyway, and I unlinked it from the system. So yeah, go to the manufacturer. That's a good point, Felix. Thanks for the feedback. So in any case, you can, you pick the, yeah, you're right, Don. So medium voltage still, I mean, hopefully we'll get some momentum around medium voltage in the National Electrical Code. But in any case, so that's what I'm doing on the impedance values for the conductor. So I basically just went out, but you'll either use what's in the library or grab it from the manufacturer of the cable, or go back to the National Electrical Code if it's a 600 volt cable. So as long as you meet the right criteria, you're going to get in the ballpark. But as we saw, slight change in impedance of conductors, because they could be long runs, could make a difference. Okay, transformer impedances. I used 5.75%, and I used an X to R ratio of 6.15. What you can do, I don't know if y'all know or familiar with this book. This is the IEEE Red Book, and this was mine from 1986 when I bought it. Actually, I bought this around 1989, and I bought a whole set of color books because the gentleman I worked for lent me his, and as I read through these and I used it to do my first short circuit study, these books are they're just, you got to have a copy of them. So any chance you get a copy of IEEE Standard 141, and there's different versions. My personal preference is the 1986 version, the earlier versions, because there were some nice diagrams that for some reason were removed, and physics doesn't change, but in any case, what you'll notice in here is they have some tables in the back of chapter 6, I believe it is. Yep, chapter 6. After they do a sample calculation with you, which is really cool. So you could copy the one-line diagram, do your own. You can do my diagram because I did all the numbers for you. If you don't have SKM, you at least know what the numbers should be. You can run it by hand if you want to and see if you can get in the right ballpark. But if you go to the end of this document, there are some curves. I'm looking for it. Yeah, here they are. So they have X to R ratios of transformers. So if you don't have an X to R ratio on the transformer you're dealing with, and these are based on ANSI IEEE standard C37.010, and I have a copy of that. I'm not going to show it to you because you're going to buy a copy. I don't want IEEE yelling at me. So they have a table in here. They have a typical X to R ratio, and this is for self-cooled transformer ratings in MVA. They have an X to R ratio for small generators. They have an X to R ratio for three-phase induction motors. So if you're not sure of the X to R ratio, and a lot of cases will just ignore the resistance, because the only reason you need the X to R ratio is to model an R plus a JX. In many cases, to simplify things, from a transformer perspective, it's a J at the impedance. So we ignore the resistance. If you do want to get down to an X to R ratio, references like the Red Book, IEEE standard C37.010, and there's a few other references, but they pretty much all go back to the transformer standard. We'll tell you some ballpark figures for X to R. The reason that ignoring resistance is not a bad thing is for a couple things, a couple reasons. One, if you think about the impedance, if you think about the impedance diagram, right? You have the power triangle, and we had this was wasting paper. There we go. That was R, and this was X, right? And that was our angle, our theta. The reason, what we'll do is we'll use X. That hypotenuse is going to be a bigger number than X. X is going to be a smaller number. So if I'm using just X and ignoring the Z and not using Z and at the angle, not doing the complicated math, I make this so a 5.75% transformer would be a J 0.0575 and no resistance. That number is going to be smaller than incorporating the R, so my fault currents will be inflated a little bit. And when we start talking X to R ratios, and when I'm picking my overcurrent protective devices, the higher the X to R ratio, the harder it is for, say, a circuit breaker to trip, so or to clear that fault because of, and we'll talk a little bit about the X to R ratios and how circuit breakers are tested. That's why I got Lou Grayhor in the house. He's my safety blanket with regard to making sure I'm 100% accurate on that. But if I throw in a bunch of X and I ignore the R, then my X to R ratio, my X is going to be bigger. So I am conservative. My fault currents are going to be conservatively high. And if I'm using it for interrupting ratings and short circuit current ratings, that's a good thing. My X to R ratio is going to be conservatively high. So if I'm trying to make sure that I don't have an X to R ratio at any overcurrent device that they can't handle or haven't been tested for, I'm going to be good. If I get close, if I go, wow, my fault current is really close, I'm going to throw the R's back in, see if it helps me. Or if my X to R ratio doesn't look that good, I'm going to throw some more R's in and do those X to R ratios. So, but many times, motors will just use the Z, just the X value. Transformers will just use the X value, not the R. Even generators, subtransient reactance, that's what we use. We won't use the X to R ratio. But that's just, that's rules of thumb. You're the engineer. You take the avenue that you want to take based upon what you're trying to achieve. If it's interrupting ratings, if you use X's and forget about the R's and don't do the complicated math for certain component, can't do that for a conductor. You're going to need that R value. That's where that's significant for conductors. But the R values are going to be pretty small for things like transformers. That big iron hunk is a burning love, right? That's just one big hunk of iron. All right, so I'm just going to make sure I'm taking my little checklist. So we talked a little bit about per unit. We got the base values discussed, answered some of those questions. Talked a little bit about where we're getting our impedance values. So I'm going to talk the impedance values. The conductors, we already saw where we got now the other thing on the transformers, 5.75%. The thing to remember too about a transformer, I don't know if I have my slides over here. Just check. Yeah, I do. So there's your C57.12.36. That's the standard requirements for liquid immersed distribution substation transformers. And you'll see where they have the percent impedances. This gives you your, look at the, what do we have, a 1500 kVA? If you look over here, you've got 750 to 4999. Now this is, again, this was liquid filled, right? Yeah, liquid immersed. Look at the impedance, 5.75, 5.75 on the low voltage side, 600 volts and below, and then 600 volts above 600 volts. So I could, if I have different, like the 112.5 to 749, you're still at 575, but then it could go as low as 1.7. Now, the other thing to remember is there are tolerances on these. So even though I mark my transformer at 5 point whatever percentage, I can be plus or minus. And these standards help me understand the pluses and minuses. And why would that make a difference? Well, if I'm minus 10% of 5.75, if I'm worried about having the highest available fault current, I'm going to run my short circuit study. I'm going to take the 5.75 and I'm going to take it at 90% of 5.75 and use that. That'll give me a lower impedance value. That'll give me a higher fault current, just in case my transformer is on that lower end of the band. Remember, we're manufacturing a big hunk of iron and we're wrapping copper around it. So, I mean, we're not into the 2 decimal points on accuracy of our label. I'm telling you. So we just know this is supposed to be a 5.75 when we make it and we test it. We make sure we're in that tolerance range. So what you're going to do typically is, and I believe SKM and other programs will do this for you, but you got to typically tell it to do that. Otherwise, it's going to use the exact values that you have. So here's sort of some from those standards. 9.2, the impedance of a 2-winding transformer with impedance voltage larger than 2.5% shall have a tolerance of plus or minus 7.5% of the specified value. And tolerance for those with impedance voltage of 2.5% or less shall have a tolerance of plus or minus 10% of the specified value. So these percentages, and this is a tolerance, so you got to be mindful of that, especially, I think, more so, in my opinion, if you are cutting it so close that the percentage of your transformer is going to determine whether or not you bought a 65K breaker or a 100K or a 22K versus a 42K, you're cutting it too close, in my opinion. Bump that interrupting rating up for a couple reasons. One, you're not designing for today. You're going to be designing for later on as well. So if things change, if anybody adds motors, subtracts motors, adds another source of available fault current to the power distribution system, you don't want them to have to change out equipment. They're going to have to do the short circuit study again, but you're not going to want them to have to change out equipment. Lou Greyhorse says table 4-2 and table 4-3 of AB3 has info on power factor and X to R correction factors. Yes. May not match new transformers design. So yeah, that's true, Ahmed. So what you're going to want to do, or I don't, I'll call you AM. All right. So what I would suggest, now remember, if I'm in the design phase, I haven't picked a vendor, but I need to go out for quote. And I'm telling you, if you tell my sales guy I need a circuit breaker and you don't specify what type of interrupting ratings you're looking for, I'm not going to come to the table with a number that's at 65K or 100K or 200K. I'm going to come to the table with a 10K number until you tell me you need something bigger. So it's important in the specifications that you say, look, I need 65K breakers here. I need 22K breakers there. I'm good with 10K breakers here, or I need a 200,000 amp interrupting device up here. So you're going to need to know your fault currents throughout the power distribution system. I know a lot of engineers who will just swag at it, and they'll say, well, for example, on the secondary of any transformer, you can do an infinite bus calculation and you're in the ballpark. And if you're below 10,000 amps right at the secondary of that transformer, then you don't need to do anything further. You buy 10K breakers. If you're less than 22 but greater than 10K, you're buying 22K breakers because you know it's going to be something less when you start adding impedance. So there are some things you can do to get you in the ballpark. But the good thing, it's worth spending some time if you are a design build kind of guy, or if you're a design engineer, to start getting things into your program of choice, whether it be SKM, EDSA, Easy Power. Get your young engineers involved. Have them be put together the single line diagram in SKM, and using some ballpark figures, you can give them some numbers. That'll give them experience with creating the models. And then because you're going to want to do an arc flash analysis study, you're going to hopefully be in a labeled environment, and you're going to help your customer understand the importance of a labeled environment for electrical workers and the importance of understanding things like incident energy, available fault currents. You might have to do a motor starting study depending upon the application as well. And we're going to do one of those So added contribution from motors. Exactly, Michael. So when you start adding, here's the other thing. Oh, man, Michael, good point. And I'll have a lot of people use series-rated circuit breakers. And I did a program in Alabama one time, and I was teaching on the difference between a series-rated and fully rated overcurrent devices. And if you think about a series-rated overcurrent protected device, what is a series-rated overcurrent protected device? That is when you have two circuit breakers in series with each other, and say this is at 10K interrupting rating, and this is at 65K interrupting rating, and say my available fault current is 50,000 amps. If I didn't have a series rated system, I would say this 10,000 amp interrupting rated circuit breaker is being overdutied because you're going to ask it to interrupt current higher than what it's rated for. But in a series rated system, what we'll do is we test both of these devices together, and we can tell you that the 65K will open and the 10K will open, and they will successfully clear the fault together. Teamwork. Sort of like what we're doing here. Michael, adding some information. We're exploring this discussion. We're learning together. So 65K and 10K, that's a series rated system. But, so I was doing a presentation down in Alabama and I was explaining this. And now let's say, for example, I put a motor contribution in here. And there are a lot of engineers that miss this. And this one gentleman in my class came up to me afterwards and he said, Tom, I have a problem. And I said, what's the problem? And he says, you know, I didn't know about the series ratings. And based upon your presentation, I have a lot of projects that are violating the National Electrical Code requirements on series rated devices. Here's what his problem was. If you think about the current flow for a fault, say here, I will have current flowing from the source through the 65K breaker and the 10K breaker. But I will also get current that flows from the motor. This motor contribution does not flow through the 65K breaker. That 65K breaker is not going to see it. Why? Because electrons are party animals, and they are freaking lazy. They all want to go to the party. The motor, what does a motor do? When you collapse voltage and it's still turning, it turns into a generator. So you're going to have motor contribution. And it's lazy, so it's not going to go back up towards the system because everybody's heading to the party right here. So no current flows through the 65K breaker, but more current will flow through the 10K breaker. So the National Electrical Code gives us a, and this is this is my panel, and I should know the section. Now, Don Ganier's out there. Don will know the section right off the bat. But in any case, I got to find the series rated the series rated. Is it in 240.83? Nope, it's not in 240.86 series ratings. I knew it was around the 80s somewhere. So 240.86 tells us where a circuit breaker is used on a circuit having an available fault current higher than the marked interrupting rating, which is what we got here, by being connected to the load side of an approved overcurrent protective device having a higher rating, which is this guy up here. The circuit breaker shall meet the requirements as in A or B and C. So you got to do A or B and C. A just talks about engineering supervision and engineering a series rating. B tells you using tested pairs, and we'll publish those. Like I say, we test these things together. C talks about motor contribution, and everybody forgets about C. We love why do we use a series rated? Because why? I don't want to spend the money on a 65K rated branch or feeder device. I just don't want to spend the bucks. I would love to sell you one of those. But if you meet the rules, you don't need to. You can do a series rated system, but you got to meet the rules. And everybody says, oh, I can do a series rated, and I use the tables. I'm done. Go away. And they forget about the motor contribution. So here's what it says about motor contribution. Series ratings shall not be used where, 1, motor circuits are connected between, now this is the 2020 code, and we actually are looking at modifying this a little bit more in the 2023, trying to add clarity because people are screwing this up. Motor circuits are connected between the higher rated overcurrent device of a series rated combination and on the lower rated circuit breaker. Where's this motor? It's between the higher rated overcurrent protected device and the lower rated circuit device. Why is that important? Because motor contribution is going to flow through the downstream, but not the upstream. How do you think I tested this in a lab? Lou Grayhor can confirm this. We tested 2 breakers in series. We don't have a motor inside of our lab, and when we test these things, and again, Lou, I hope you're there, correct me if I'm wrong, we don't generate a motor and generate motor contribution. We will pump current through both of these as they are in series. So when you start adding a motor, you start getting outside of the area of how they're tested. So we have a comfort zone, and we put some error margins in here, and what we say is, the sum of these motor full load currents exceeds 1% of the interrupting rating of the lower rated circuit breaker. So 1% of 10,000 amps. What's 1%? You gotta do the math. Real easy math. 100 amps? 10%? Is it 1%? 1%. So you don't have much motor contribution to get you out of being able to use a series rated system. And the gentleman who came up to me at that class, when he told me that he thinks he's violating that, my comment was, I said, well, is it a commercial building? Because, you know, commercial buildings, you can add up all these small motors. You're not like an industrial facility where you have these big motors. And he says, I'm a car wash station. Because I design car wash stations. And we're all motors. And some big uns. You know, in West Virginia, we call them big uns. So he was violating the National Electrical Code 24086.c. And I think there's a lot of applications out there that violate this. And it's probably just a matter of time before a fault occurs, and your estimates were, and you bought the you had just enough fault current to give you a headache, and you know what we call that? An unintended rapid disassembly in the field. So it's another good one. That's a Dan Neeserism. I think it's a Dan Neeserism. I'm going to give him credit for it, whether it's his or not. So in any case, motor contribution is really important, and why the series rated systems can sneak up and bite you if you're not careful. And I always tell people, if you're trying to save money, if you don't want to buy my 65K breaker and you want to buy a 10K breaker and you want to leverage this, I'm okay with that. Cross your T's and dot your I's. Anytime you want to save money, I don't care. Think about it. You're going to go down to, you're going to go buy an inexpensive piece of equipment. And, maybe for the job that you have, you should have spent a little bit more money, So make sure that whenever you're trying to save money, you're following all the rules. All right, so there's an auto transformers, again, plus or minus 10%. So and then there's UL 1561. This is the standard for dry type, general purpose power and power transformers. Look, now that was the liquid filled, the previous one. This is the dry type. Dry type, the marked value is acceptable if it is within plus or minus 10% of the determined value. So I can mark that transformer with a number, but I got to be within plus or minus 10%. If I'm doing an incident energy analysis, I'm going to add 10% and subtract 10%. I'm going to run them both ways. If I'm only worried about interrupting ratings, I'm going to use the lower end than of the 10% and knock that off my impedance to get a higher value of fault current. So now the transformers should be marked, but again, what you can do is, let's do this. We're going to do this together. because we're together kind of people. So we're going to come over here and we're going to say Eaton. Look at Eaton transformer impedances. Distribution, dry type, low voltage transformers, transformer nameplate impedance. So let's open this one first. If I look at this and I'm going to do a search, Control F for impedance. And I think I got to go forward a couple places, special impedance. So we can also, if you need a specific impedance, we can make you a transformer with that specific impedance. So be mindful of that. We have I call it the custom shop. I don't know what the formal Eaton name is for it, but I call it the Eaton Custom Shop because I think of the Colt Firearms Custom Shop or the Remington Custom Shop. You know, if you want a custom-made firearm, or even the Gibson Custom Shop, where you can get a custom-made guitar. All right, look at this. So here we go. We have a KVA. We have the frame. We have the weight. We can tell you how much it weighs, the losses in the weight. We got percent regulation. And look, this column right over here above my head is impedance, a minimum and a maximum. And then you look down here, actual impedances may vary plus or minus 7.5%. So we'll give you some ballpark figures that you can use. And if you're not sure, you haven't bought the transformer yet, it hasn't shown up on site, you haven't done your as-builts, you can use this type of information to get you in the ballpark, especially if you're buying it from us. I don't think anybody else makes transformers. I think it's only Eaton, if I'm not mistaken. But in any case, depending on who you're getting the transformer from, they'll publish information like this, and you can plug both of these numbers in. In fact, you could add these right into your SKM or EDSA or Easy Power libraries, so that you're using these things. So we have tables for different types of transformers and impedance values for all of those, and efficiency numbers. So there's a lot of it. Now there was another link over here too. Let's open this one. This is a good one because what I like about this is Dave Laux, Dr. Laux, wrote this that talks about transformer nameplate impedance per unit versus absolute. Apparently there you could possibly buy transformers that have absolute values on their nameplate. So this is a really good document. I'll put both of these links. You know what I'll do is I'll do this right now. I'm going to put this link, Control C, into the chat box. Hey, Felix. Yeah, brother. There's the one and the only. There can be only one. That was a good movie, if anybody remembers that one. I'm going to grab this one, Control C. I'll put this one in there too. So there's both of my references are in the chat that I just called up. But in any case, this is it's a good white paper that talks about percent impedances of transformers and all that good stuff. So for your reading pleasure. But the standards also give us some guidance and all this other good stuff. There's that. So there's the figure 4A-1. This gives you the typical X to R ratios. Thanks, Ryan, 240.86. This will give you the typical X to R ratios. And here's another one, C37.010 on 2016 version. Here's the X to R ratio for power transformers at 60 hertz. It gives you a low and a high. And again, rarely do we model X to R. I modeled it, and I wanted to because I wanted to teach you guys about complex variables. So that was just I think SKM will automatically put that in there, and I wanted to try to get as close as I could to show you the hand calculation matches what the SKM is putting out. So we're doing it right. If we were just using X's, we would be a little bit further off. We'd have a little bit higher of a fault current value, and you don't know if you're screwing up a zero in there somewhere or what. So I wanted to make them as close as possible as I can. There's where I got the conductor. Remember the ohms per 1,000 foot. This is out of the code book. You got the size, and remember we talked about there's your X sub L. That's your reactance for all of your wires. and there are your values. The top number is your kilometers, ohms to neutral per kilometer. The bottom number is your ohms per 1,000 foot. I used ohms per 1,000 foot. I haven't gotten into the kilometer world yet. And then there's your AC resistance for uncoated, and then aluminum and copper wires. And that's your impedance values. And you can always take a look at that. And I'm not going to go through all of the notes and whatnot, but you can read through the notes. I'd read through the notes if I were you and take a look at that. And all I'm doing here is showing you some of the numbers that for a 2-aught conductor. I don't know if I used that in my example, but this is the math I used to get you to an ohms instead of an ohms per 1,000 foot. You take the length over 1,000 foot. And that's how we model the conductor as a resistance and an impedance in series with each other. And so that's where you're getting your power factor from. And remember, if I'm not doing my X to R ratios for transformers and motors, I'm having more X. The R from a conductor is what's going to help that circuit breaker infuse in their interrupting capabilities. All right, so this is just SKM. That's sort of what I'm doing there. Fault currents may change. Now let's talk about changing fault currents, because this is another pet peeve of mine. Let's go back to the one-line diagram, the impedance diagram. If you think about the impedance diagram, this was our impedance diagram. If you recall, the very top was the utility, 125,000 amps, and we converted that to an impedance using per unit. So these were all of our impedance values. If I want to assume an infinite bus, I'll tell you what I do. I will tell you what I do. For an infinite bus calculation, I'm just going to copy this slide. And I'm going to go to the next slide over here. So here's what I do. I take the utility impedance. Now this is what infinite bus is all about. Watch the utility impedance. Boom. Goes away. So I have basically zero impedance from my utility. With zero impedance, I'm going to get all the fault current I can get, right? So I have nothing bringing my, remember, impedance will lower fault current. If I take the utility out of the picture, that's an infinite bus calculation. So what I'm going to run is I'm going to take this out of the picture, and I will leave this, but let's just do the math real quick on, we're going to add those three impedances together, 0.002. Actually, what I'll do is I'll show you on my, with my calculator. I don't know if you have an HP or whatnot, but you can take those three impedances. Let's put these three impedances down. What do we got? We have 0.0003 at an angle of 45. We have 0.0575, that's our transformer, at 80.76. And we have 0.001 at an angle of 66.04. And that is our 1 per unit voltage. And these are all in per unit. So now what you can do to add these up, I'll show you how I do it on my calculator. I can see this. So I take 0.003, 0.0003. I hit this blue key, and I hit the angle theta, which is right below the I. And you'll see it has a theta right there. And I put the angle in, 45, and I hit enter. So that is 0.0003 at an angle 45. Then I do 0.0575 at an angle 80.76, and I hit plus. And then I take 0.001 at an angle of 66.04, and I hit plus. And there's my total. My total equivalent impedance here is 0.0587 at an angle of 80.34. Now to get my I per unit, I take 1 over that 0.0587. I do 1 over, and that is 17.03 at an angle of negative 80.36 because the angle was in the denominator. I'm looking over here, you're over there. Okay, so that's in per unit. Where is this at? This is at the 480 volt. This is the secondary of that 1500 kVA transformer. My I base is 1804.22. Okay, because that's the full load amps of a 1500 kVA transformer at 480 volts. So I take 17.03 times 1804.22, and that is, I take 17.03 multiplied by 1804.1804.22, 30,726. 726 amps. All right, so what we're going to do, now what we did, what was the number before? Let's go to SKM. Right, so I'm at SKM. I have, my motor is disabled. I'm going to run my balanced study. I hit run, close. My fault current is 12,958. No, I'm sorry. We're at bus A. Like, man, that's low. 29,872. And that is with the utility. Now, what did we calculate? 30,726. And this was 29,872. I took 125,000 amps away. And I went to infinite, right? So 30,726 minus 29,872. That is a difference of 854 amps. So 854 amps. Think about my available fault current swung from infinite to 150,000. So let's do this. I'm going to go back over to SKM. And this is why I love when someone says, you can't mark the available fault current on equipment because the utility's fault current is going to change and all your numbers are going to be wrong. Whoopee, ding, ding. So anyway, this is 125,000 amps. Now to do an infinite bus, I check this box, infinite bus. Now it's going to ignore everything and I'm going to run my numbers again. And we're going to see what 29,000 amps does, right? So we're going to do a run, balance study, run, Forrest, run. 30,718. Ooh. And what did we calculate? 30,726. 30,718. We're off by 8 amps. 8 amps. Sweet. So now that's an infinite bus. Let's put this back at, we'll say 65,000 amps. Oops. Take the infinite bus off and we'll make this 65,000 amps. Okay. 65,000 amps. I'm getting a red. I'm not sure why. Hold on. Update. 65,000 amps. Jeez. Numbers there. All right. So let's go back up to here again. My utility, infinite bus, 65,000 amps, run balance system. Rounding error. Don't be too hard on yourself. That's exactly, yeah. Input data. Apology not defined. Hold on. Let me do this. Nope. I'm going to start that again. I hit a button. I don't know what I did. I was looking, so I'm gonna reopen it up and see if we can make that change again. All right. So no, it already did it. Okay. So let's go back to this again. Angle 1 in service. Here's what I'm going to do. I'm going to delete this. Destroy. Okay, I'm going to add another utility in. Utility. You zoom in. Okay, so I don't know what I did, but I did it. Okay, so I'm going to make this 65,000 amps. Let's say that the utility tells you that you've got 65,000 amps available fault current. And we're going to look at bus 4, and we're going to do a calculation. Run, balance study, run. Close. 29,132 amps. So let's say that the utility decides that they're going to give you 200,000 amps. 200 and 000. I want to make sure I get the right numbers. So now the utility is going to bump you up to 200,000 amps from 65,000 amps. What's this number? Let's write it down. That number is 29,132 amps. Okay, and overnight they made a change. Run, balance system study, run, close. And you went from 29,132 to 30,184. So 30,184, 29,132 minus, it went up 1,000 amps. In my opinion, 1,000 amps is nothing. I mean, it's 1,000 amps, but your available fault current, think about it. I went from 65,000 amps to 200,000 amps. I added, let's take this to, let's say that this, instead of 200,000, we went from 65,000 to 100,000. And let's run the number. Run, balanced, run, forced, run. And 29,668. So we went from 29,132 to 29,668. Whoopee ding ding, right? So to say you should not mark the available fault currents because the utility fault currents could change and your numbers are going to be wrong, you're going to be off a couple hundred amps, which I could be off a couple hundred amps based upon a couple assumptions that I made. Now, where it might make a difference is on this side of your main transformer, where you're coming from the utility. Remember, I went from 65,000 to 100,000, 65,000 to 200,000. It did not impact very much on the secondary of this transformer because that transformer is one big hunk of impedance as compared to the utility equivalent impedance. In fact, let's go back over here. Right, so let's take a look. What's the impedance of that transformer? 0.0575. What's the source utility impedance? 0.0017. The source impedance from the utility is very small as compared to that big iron transformer that you have out in front of your facility. So changing fault current on the primary of that transformer does not really significantly impact the secondary. So in many cases, what will we do? We'll just do an infinite bus calculation, forget about the utility. Regardless of what they do, whatever they do, they're going to bring it down by a few hundred amps. You're picking over current devices for their interrupting range. You're not worried about a few hundred amps. Okay, you shouldn't be, because if you are, you're not doing a good design because you're not thinking about the future. You're not thinking about motor contribution and all the other great things that Michael pointed out as well. So full load current divided by percent impedance. Exactly. So if I did that transformer, full load amps over percent impedance, that will tell me the, so if I wanted to know the available fault current before conductor 2, right? So I take this out, I'm taking conductor 1 out of the picture. If I just looked at the impedance of this transformer, that's going to tell me the available fault current right at the secondary, the maximum it could possibly be at the secondary of that transformer. So what is that? Full load amps of that transformer was 1804.22. So 1804.22, and you divide that by 0.0575. 0.0575 divide 31,378 amps. I can't get more than 31,378 amps on the secondary of that transformer. Am I going to put a 22K breaker in there? Probably not. Am I going to put a 65? I might put a 42K breaker interrupting rating. That gives me what? That gives me 11,000 amps to play with. And the utility changing 11,000 amps isn't going to do it. But you start adding motor contribution, you start adding motors downstream, you start changing your power distribution system, you change out your main transformer, now you're talking some significant amp values, and that's when you need to rerun those numbers. Now that available fault current at the panel boards is used for not only, there's a lot of different things that you can use it for, and we'll talk about that in other programs. What time is it? 6:10. All right. So, I wanted to cover this calculation of infinite bus, and if we go all the ways down, so what did I do? If I let's put this back at 125,000, which is where we were to begin with, and I'm going to run a number. I'm going to Control A, and I'm going to run, and we're going to write the number down all the ways down here at bus 12,958 amps down at bus 7, or our bus B. Whoop, down there. Okay, so that's bus B down there, and that is 12,958. I wrote. Now I'm going to go back up to the utility, and I'm going to put this at an infinite bus. Oop. I just double click, I select infinite bus, close, run, balanced, run, close, and we scroll down, and our fault current down now is 13,025. So I went from 12,958 to 13,025. Again, not a very significant change when the utility changes. So if anybody ever says, hey, utilities change their fault currents all the time, all your numbers are wrong. By how much? And is it significant enough to even worry about? You change out that transformer, I'll change your fault currents, buddy. You add some motors, we'll change your fault currents. But changing this utility. Now, if I was on a secondary network, before these transformers, yeah, you go from 65 to 200,000 amps, whatever is between that utility and that transformer, any equipment in there, that stuff's going to see a big change in short circuit currents. But once you get on the secondary of that transformer, it does the world of good. We can trust SKM results. That is the advantage of knowing how to make calculations. Felix, my goal here is to help you guys get that flavor and that understanding. Not only, every fault current analysis package out there is going to do something similar. But the cool thing is, what's going on behind the scenes. You know the importance now of that motor contribution and the fact that it is in parallel with those source impedances. If I added this motor down on bus B, I would have to put a motor from bus B in parallel with everything. That's where the motor contribution comes from. So let's talk motors. I used, what did I use? And I don't know what I was thinking. 0.15 per unit. And 0.15 per unit, and I think, Michael, you pointed it out, full load current over percent Z. So that 0.15 per unit, I'd have to take the whatever the full load amps is, but 0.15, 1 over, is 6.6 times. And and I was thinking X to R ratios. If you look at, when you get into motors and motor contribution, the standards that give you recommendations on what impedances to use, look back at what is your goal? You want to make sure that your circuit breakers and fuses can interrupt these fault currents. Your short circuit current ratings of equipment are adequate. And understanding how those products are tested is important when we start making decisions in our one-line diagram. Remember what I said, that if I ignore resistance and I just put the X for transformers, I'm conservative. Because why? Because I know how circuit breakers are tested. I know the circuit breaker is tested with a specific X to R ratio. And in fact, if you go to remember that, which I don't know if I put a link to this out there or not. I'll try to find it online. But I'm going to search my consulting application guide. Whoops. Not X over or, X to R. In here it is. Look at this. So based on the use of an XR ratio of 6.6, representing a source short circuit power factor of 15%. If you look at how we test our overcurrent protective devices, well, you know what I do? I have it in my PowerPoint. What am I talking about? I do go over this. I think it's in my X to R. Here we go. So if I look at this table, this will show you the X to R range that we test over molded case circuit breakers. If the interrupting rating is 10,000 or less, your X to R ratio is somewhere between 1.98 and 1.73. If you're over 10,000 up to 20,000 amps of interrupting rating, you're at an X to R of 3.87 to 3.18. And if you're over 20, then you're at a 6.6 to 4.9 in that ballpark. So 6.6, that 0.15 power factor is where you're at. Now let's take a look at, and why is that important? So before we take a look at our impedance diagram, let's just talk about why that is important. And I briefly covered this last Thursday. But if you look at the sine waves and you look at, like, this is an X to R ratio of 0.4. Your current and your voltage are very close in sync with each other. Your current is lagging your voltage by a little bit. This is at 0.8. A lot of power systems are at around a 0.8, 0.85, or 0.9 power factor. Your angle's at 36.87. Your X to R is 0.75, so it's a low X to R ratio. When your X to R ratio starts to increase, your power factor is decreasing, meaning my sine waves are separating from each other. And if I get to that 15%, look at this, look, the 25% now, when my voltage is crossing zero, my current is peak. So the higher the X to R ratio, the further apart your voltage and current sine waves are, your overcurrent device is going to have to open. But I'm trying to open this circuit breaker when my voltage sine wave is at its lowest, almost zero. My current is at maximum. So it's harder for a fuse and a circuit breaker to clear that circuit when you are when your waveforms are this far apart. We'll typically test for the worst case scenario. And if you think about, we tested what we think is the worst case scenario. But there are cases, like if you have a line reactor, you put a line reactor, a big X. What is a line reactor? It's going to be more X than R. There's going to be some resistance there, but it's going to be insignificant. So right at the secondary of a transformer, if you put a line reactor in, say, to reduce fault current so that your interrupting ratings are more, it's easier to interrupt. So you have a lower interrupting rating on an overcurrent device, you're adding a lot of X. So now you might have to derate the interrupting rating on your circuit breaker or fuse to accommodate that distance in between your the phase angle. So we offer, and we in our instructions and whatnot, we will provide multiplying factors on the interrupting ratings for these for circuit breakers that are being applied. So this is a derating factor for, if you have so you'll see here that 20%. Where's the point? There's your 15% power factor. There's your 6.6 molded case circuit breakers, and it has the separated by interrupting ratings. Now, why does that matter? If you're using a 10,000 amp interrupting rating breaker, is it right there at the utility? Probably not. What's in between you and where that breaker is? A lot of conductor. What do conductors add to the circuit? Think about our impedance diagram. There's a lot more R in a conductor as a percentage from your impedance than, say, a transformer, which is a lot more X than it has R. So you're getting your resistance value for your X to R ratios from your conductors. So when you're adding those conductors, and if you're adding conductors, that's where you're going to be knocking down your your fault currents, and you're going to get down to an X to R ratio that's a lower value. So what we can do is, let's take a look at so this is more from C37.13. So let's do this. Let's take a look at our impedance diagram. So what is the X to R ratio? So to get the X to R ratio, burning paper. What we're going to do is we're going to take the R's and X's, the 0.0002 plus J 0.0002. Wait a second. You know what? Hold on. There's one more in here. I got 0.0002 plus J 0.0017. That's the utility. This is conductor 1. Transformer 0.0092 J 0.0568. That is T1. And then you got 0.0004 J 0.0009. We're going to add those up. All right, so 0.0017 plus 0.0002 plus 0.0568 plus 0.0009 is 0.0596. 0.0596. Now we're going to add up all of our resistance. 0.0002, 0.0002, 0.092, 0.0004 is 0.0928. So this is X, this is R. My X to R ratio at that point in the power distribution system. It would help if you could see the numbers. University teaches me many things, but with your work in the videos, we really learn a lot. Thanks, Gustavo. I really appreciate the feedback, brother. All right, so now what we're going to do is take 0.0596 and divide that by 0.0928 and divide 0.6422. Is that right? R is 0.0005. C2. C1, C2. All right. That was James. All right, James. Hold on, brother. Hold on, brother, from another mother. I'm going to go back because, yeah. All right, so what you're talking about is this. Remember, right? All right. I went back and did the math. In fact, I was almost obsessed with it one night. I am going to, I created this and I'll put, I think I can, I don't know if I can share a file in the whatchamacallit or not. So here's what I got. I got this spreadsheet. And what I did here was I have utility, and I have all of my calculations. I got my base, my I base, my Z base, my I short circuit, my X to R. This is what you put in. It calculates the Z per unit and the angle, and it creates an R per unit, an X per unit, and a Z per unit. So I double checked everything after our little presentation. I know it matched SKM, but in any case, so conductors. Remember when I did this, I came up with 0.004 plus J.009. And when I did the addition, I was off by 1,000 or so amps. I'll tell you what, James, I went back and look at conductor 2. Control. So here is conductor 2. What I'm going to do is I'm going to do a freeze, view, freeze panes. So I go back to conductor 2. I have 480. That's the base values, 1804, my 0.1536. There's my R per 1,000 foot, 0.021 and 0.048. There's my length of 15 foot. 5 conductors per phase. There's my ohms, 0.0000, all those great numbers. We did all of that. Look at the R per unit that I came up with in Excel. 0.000410, 0.000938. My original number was 0.0004 plus J 0.0009. It was right. And I went back, because remember, now you think, I'm live. I got all of you out there, all you engineers checking my numbers, putting all this other stuff. The pressure was on. My original calculation, which I crossed off, was right. When I redid the numbers, I'm not sure where I made a mistake in here, but I think I made a mistake in here with the 0.0005 and the 0.0006. I didn't go back through this math. And if you downloaded that sheet, take a look at it. Do the math on your calculator. And I was, for some reason, I would do, here's what in fact, I had a phone call with Robert from Omaha called me. And he and I had a great discussion. When I was doing the math, depending upon the sequence of numbers on how I put them into my calculator, I got a couple different numbers, and I think it's because of rounding errors in the calculator, and there's ways that you can set up how many decimal points. So I think depending upon how I did the math, I was doing it left and right, and so the right number, and I'll share this spreadsheet. I don't know if I can I load file up here? I'm going to try. Control C, Control V. No, I can't. So what I'll do is I will maybe at the end of this program, I'll take some time, put it up on Dropbox, and I'll put the link. But so what this does is this spreadsheet, I calculated 0.000410, 0.000938. There's my Z per unit. There's my angle. I did all my transformer calculations, all my motors, and then in the system, I have, there's my per unit impedances, and that's from each of the spreadsheets down below. And then what this does is it adds them up. So it takes 0.00017, and which is 165. So if I bring this out and then I do this, there's my decimals. Boom, there's the 165. So to match the number of decimals, that they'll show you that the numbers are exactly the same. So this is 0.00165. There's 0.00165. And then I said this cell here is 0.00165 plus the 0.00022. So I basically added up my impedance diagram, and there's my 29872. And if I go to SKM, 29872, I'm going to make sure that I'm going to take infinite bus off, and I'm going to put 125,000 amps again. And I'm going to do a run, balanced, run. Oop, 2 fatal errors. Hold on. 125,000 amps. That off, in service. Run, balanced, run. Oh, what the heck? Let me just do a destroy, and let me add it back in again. Add a utility. Back in, utility, boom. 125,000 amps. 125,000. I remember to take that to amps. X to R of 8, which is the default value. I do a run, balanced, run, and then close, and my 29872. 29872. It is exactly the same. All rounding errors are gone. And the bus B is 12958. SKM says 12958. So by doing this in Excel, I've got as many decimal places out there. My numbers, there is not even an amp difference between what's in my Excel spreadsheet and what is in XKM. So I will make sure I put that up on Dropbox and get you that spreadsheet so you have it as part of this little program we're doing. And then you can look, and it's not a protected worksheet. So I'm going to do is I'm going to create a folder, and I'm going to call it online class create. I'm just going to put it up there right now. Did I do a Control V? Nope. I'm going to drag it over, and then I'll put the link up as we're talking. So it's copying up. So you guys will have a copy of that spreadsheet. Oh, wow, that was fast because it's very small. Copy link. And we'll put it in the chat box. Control C and Control V. There you go. So you have this spreadsheet you can download from that link. And this will be, and you know, play with it, play with the numbers, play with the spreadsheet. You'll see how I did the complex numbers and all the math. So feel free to download that and have at it, have fun. Math can be fun. Power engineering is fun, right, Felix? Okay, so all right, so I covered that. So what were we doing? We were doing the conductor too. So Michael or James, I'm not sure what I did in that calculation, and I haven't gone back over. And again, like I say, I don't know if it's a rounding error in here, but in any case, the X to R ratio, that's what we're doing. X to R is 0.6422. So am I worried about the interrupting rating? Remember, my X to R ratio, go back to, let's go back to, this is why when you read a lot of books, well, I'm not sure. It's in the red book and the buff book somewhere. But if you read a lot of books then on power systems engineering, they'll tell you that rarely do you have to compare the X to R ratios because of this, right? So the fact that we test these breakers, let me get down to where those numbers were. Now remember, I'm at 480 volt and I'm at my available fault current at bus A which is bus 4 in SKM here, my available fault current is 29,000 amps. I'm not buying a 10K breaker. What am I buying? I'm buying an over 20K interrupting rated breaker. And we test those at a 6.6 power or X to R ratio. And what was my number? 0.6422. So I don't have to worry about that. And if I go down to, if I even do, more math and add the X to R's, but that's where the X to R ratios come from. So some people will say, I don't know where to get that. If you look at, let's take a look at SKM, me and monitor 1. So if I look at SKM, if I go to Document, Reports, Text Report, and then we're going to find Short Circuit, Open. This is, I don't know if I can zoom. Can I zoom? View. I don't know how to zoom. Sorry, I can't make it any bigger. I don't know how to zoom. But you'll notice, look what it says at different bus values. Well, this says a bus value 5.82. X to R 5.95. So let's take a look at that again. Let me check my numbers. So 0.0002, 0.0002, 0.0092, 0.0004. Oh, okay, so that's 0.01. I added up wrong again. So let's do this again. You guys got to check me on this. James, where you at, brother? Huh? Where you at? Okay, so I got 0.0002. That's right. 0.0002. 0.0092. 0.0004. So if I do this again, 0.0002, 0.0002 plus 0.0092 plus 0.0004 plus 0.01. 0.01 plus J. And we're going to do this again. 0.0017, 0.0002, 0.0568, 0.0009. Okay, I'm going to add those up. 0.0017, 0.0002, 0.0568, 0.0009, 0.0596. So that's 0.0596. My X to R is 0.0596 divided by 0.01, 5.96. Yeah, that is much better. Feel more comfortable with that. And if I look at what SKM says my X to R ratio is 5.95. So I know I test those breakers over 20,000 amps at 6.6. Perfectly fine. I'm within that 6.6. Man, that was fun, right? I don't know what it is. I don't know if it's the pressure of being live or what, but I can't seem to add. So anyway, 5.95. So you get the X to R ratio from your report generated from SKM, EDSA, Easy Power, whatever tool you use. And then you get it nailed. So that's basically what you're doing, and in reality, and why a lot of power system engineering books will tell you you don't normally have to check that, because the conductor is going to get you down to your X to R ratio that you need. So I wouldn't. What I used to do is I would just do a cursory check. I just scream down through and look for anything greater than 6.6. Now, if I'm further down in the power distribution system where I'm buying 10K breakers, I'm not worried about being above 6.6. 6.6 is right there at the tail end of a transformer. Think about, just think about this transformer. What's this transformer? It's 0.0568. 0.0568 divided by 0.0092. 6.17. So right there at that transformer, I have 6.17 minus anything else. So not including any conductor. So I'm not going to be greater than 6.6. You've got to have the right mix. Maybe you have an inductor in there. If you've got some crazy power distribution system stuff going on, you've got line reactors, things like that to knock down fault currents, you might have to worry about your X to R ratios with respect to the overcurrent protected devices. But my thought process is, if you're a power systems engineer, if you are worth your salt, you're not going to give the deer in the headlight stare when someone says, did you consider the X to R ratio? Right? You can spout off and say, hey, yeah, you know what? I'm not typically having to worry about this. I'm not using any line reactors. I'm not right there at the secondary of the transformer. You know the conductors are going to knock that X to R ratio, and all I got to be is below 6.6 for greater than 20,000 amps interrupting rating. And you know what they're going to do? They're going to go, okay, next, and they're going to walk away because they're going to go, this guy knows his stuff, right? And what you're going to do with your power systems analysis studies, you're going to scan down through there pretty doggone quick, look for anything greater than 6.6. Because this is going to give you a available fault current at every one of your buses in your power distribution system. So I'm not sure if the software will flag them. I don't know. I never relied on the software to flag issues. Just never did. I always had that covered in my report. So everybody's different. So anyway. All right. So let me look back. So we covered the X to R ratios. I feel good. Hopefully you feel good about that. Talked about per unit. We talked about complex variables. I'm going to hit that real quick. We talked about motor contribution, motor impedances. Usually on motors, I used that's where we started. We were going on that road. I used 0.15. And 6.6, 0.15, bring that to the numerator, and 1 over 0.15 is 6.6 times the available fault current. And if you look at some of these here, my red book, IEEE standard 141, this is this section here, 6 point whatever, talks about, see, here's the important part. When they talk about motor contribution, they reference circuit breaker and fuse standards as to what a circuit breaker and fuse. That's how we got into the whole X to R discussion. Because if you look at 6541, talks about for calculations of short circuit duties to compare the interrupting ratings of low and high voltage fuses, and I can say circuit breakers as well. Oh yeah, it does, and then circuit breakers. Subtransient reactances are used to represent all rotating machines in the equivalent network. The subtransient reactance, remember, a motor is going to change its impedance dynamically based upon time. So when you collapse that voltage, the first so many cycles is going to be subtransient reactance. And then it goes to transient reactance. Then you're just to the reactance. So you're modeling what the output of that motor is going to be based upon the time and what happens. Now, what this document tells us, and I think I tore this off somewhere, but it says usually you use 4 times rated for induction motors and motors in general. So what you'll do on the motors is you'll, above like if I had a 300 horsepower motor, I'd model it. But sometimes you might see on a one-line diagram, it'll say 300 horsepower of motors less than 50 horsepower. You basically just say how many motors do you have less than 50, add them all up, and then you include that as one lump sum somewhere on the different in your power distribution system. And typically we use 4 times. And if you think if you do 4 times the full load amps, 1 over 4 is 0.25. So 0.25 subtransient reactance is typically what we use. It says the 4 times rated current short circuit contribution estimate is determined approximately in the low voltage circuit breaker application guide, ANSI IEEE C37.13. by assuming a typical connected group of having 75% induction motors at a 3.6 at 3.6 times the full load amps, and 25% synchronous motors at 4.8 times rated full load amps. So what they're saying is, you might have induction motors, you might have synchronous motors. An induction motor is typically at 3.6 times the rated current, which 3.6 times the rated current would be a subtransient reactance of 1 over 3.6, which is 0.2778. So you might model it at 0.2778 if you say that's an induction motor, which is bizarre why I used 0.15. I don't know. Again, it was an operation of math. That's my excuse. I'm sticking to it. But what they'll say is you're not sure how many synchronous motors, how many induction motors are out there. So they make an assumption, and there's various assumptions. You'll find different reference books. They'll tell you for a commercial building, you can assume this percentage of induction versus this percentage of synchronous. For a heavy industrial, you'll have a different percentage value. So, and the more intimate you become with the power system that you're designing, you'll know exactly how many induction motors you have, and synchronous motors, pretty much, outside of the small piddly ones, which you don't have to even worry about. You don't have to worry about ceiling fans or motors. You don't worry about motor contribution for fault current from a freaking ceiling fan. Just saying. If you do, you need help. Anyway, 4 times. So this is telling you 75% induction motors at 3.6 and 25% synchronous motors at 4.8 times rate. And then it says, to simplify comprehensive industrial system calculations, a single combination first cycle network is recommended to replace the 2 different networks just described. It is based on the following interpretation of referenced standards. Because the initial symmetrical RMS magnitude of current contributed to terminal short circuit might be 6 times rated for typical induction motors, using 4.8 times rated current first cycle estimate for the large low voltage induction motors. Those are all motors 50 horsepower and above. Effectively the same as multiplying the subtransient impedance by approximately 1.2. So what they'll do down below is they'll give you different multiplying factors for the types of motors as well. So in any case, this IEEE Red Book, the IEEE Buff Book, and they're updating all of these. There's new IEEE standards for these. All great references for you. But if you looked at the Beeman Handbook, they would have the same information, and a few other references will give you similar, and they all quote that C57 document. So just remember those. What else? All right, so that's the motor contribution. We talked transformers, all that good stuff. We talked about the infinite bus. I'm going to end this on the last 10 minutes. I just want to do a little overview of complex numbers, because we use them a lot. And I know that we talked about this last week about representing impedances, real and reactive, as R and X, and I threw in this J operator, but I wanted to at least walk through some of our numbers so at least you have it. How would you approach a 50 horsepower main fire pump connected to a controller where a breaker is not allowed between the pump and the controller for fault current? Breaker doesn't impact the fault current. Remember that. You're still looking at that 50 horsepower motor. You're looking at estimating, if you have the motor, it'll tell you what the subtransient reactance is. What you could do is go to that motor manufacturer and say, what's a typical subtransient reactance? To model that fire pump motor. The breaker, the breaker is not going to change your fault current. That's why if you take a look at my single line diagram, my impedance diagram, all my breakers are gone. All my fuses are gone. I modeled each of those impedances. I don't model the impedance of a breaker or whatnot. So for that motor contribution, it's the same as you would any 50 horsepower motor. You're going to look at this. If you don't have an X to R ratio from the manufacturer, you can go to the IEEE documents and find what's that ballpark figure that they use. And you very well, you could model it as 0.25. If you go to a lower number, it'll increase the impedance because remember, you have impedances in parallel. So I would fall back on that on that and that other impedance. Hey, thanks for joining, Ryan. And I know we're getting close to 7 o'clock. I got 10 minutes. So thanks if you're dropping off. Thanks for joining, Felix Sandoval, all you guys. I really appreciate you hanging in there for these 2 hours. So I'm going to walk through some of this and talk about it very briefly. We talked about this yesterday. My R and my X, I can, if I know any couple of these values, if I know the Z and the angle, I can calculate R and X. If I know R and X, I can calculate Z and my angle using these standard equations. So I know the magnitude of Z is R squared plus X squared, square root of that. That's given. I can represent this as coordinates. Now, if you think about, you got to think about this in a 2-dimensional, not a 3-dimensional, but 2-dimensional. You have an x-axis that goes negative and plus. You have a y-axis that goes plus and negative. I can take and represent this as a vector looking at P, and I have to realize that that triangle can be in any 4-quadrant. I can have a triangle that looks this way, where my x is negative. When my x is positive, that's an inductive load. When my x is negative, that's a capacitive load. I'm going to talk about that later. When I get into this quadrant or this quadrant, that's when I'm doing my math and all of my angles are working out, when I'm multiplying numbers, adding numbers, and all that good stuff. Now, let's talk about this. That imaginary number, I use it, J. You may have heard it called I. You may have heard it called A. But I'm going to call it the imaginary operator. The imaginary operator, I'm going to do 10 minutes on complex variables, and you ain't going to see anything better than this. I don't think, if I say so myself. That imaginary operator is a number, and it has values. It helps me identify what is a real component, the resistive component. That's where we get our watts from. And what is the imaginary component? That is the X. That's our reactance. That's where we get our VARs from, right? And together, this all makes power factor. That imaginary unit is a number that if I square J, it's a -1. If I cube J, it's a -J. Because think about it. Square root of J is a -1 times J. It's a -J. If J to the 4th is 1. Why? Because it's J squared, and a J squared, 2 -1s make a +1. 1 over J is a -J. J over J squared is a -J, and 1 over J squared is a -1. Pause this, write them down, because if you get into the details, if you get into your a PE exam or whatnot, you may have to know some of this math and how to handle J squareds, J cubes, 1 over J's. This little key is going to be key, possibly on your PE exam later on. Now, this is X. That X is positive, and that is J omega L, 2 pi F times your inductance. That's an inductive load. Now, you may say, well, Tom, I thought that an inductive load had a lagging power factor. Why is theta positive? A cosine of theta is going to give me a positive number. That gives me a leading power factor. But remember, I is V over R. And remember, when we divide complex numbers, when I put an angle on the denominator, I'm subtracting the angle. So it's going to be negative theta. So when I do my cosines and whatnot, that'll be a lagging power factor. Even though my X is a positive number in an inductive load, it's still, when you do the division, it puts it at negative. And the angle will become negative. Now, when I do capacitive, remember, X is 1 over J omega C. And if you remember from those previous equations, 1 over J is a -J. So if you saw this on a quiz, on a test, on somewhere, and you had 1 over J omega C, and they told you what the resistance was, and they tell you what the X is 1 over J omega C, and you've got to add those things together, remember, it is -J times 1 over omega C. That's how you're going to combine these and make your impedances. And the angle, because it's a -J, goes negative on your axis, on your vertical axis. So a capacitive circuit is going to have a positive current angle. It's going to be a leading power factor, and we're going to talk about power factor in a future session. So these are some of the key equations that you'll need. You're going to write those down, or pause this, write them down, pause it, write the others down. The magnitude of z is the x squared plus r squared square root, and you have an angle. That's polar coordinates. We talked about polar coordinates, and it's basically representing z at an angle. It's called a phasor. And I can get my r's and x's from z cosine theta or z sine theta. Z sine theta gives me x, z cosine theta gives me r. And then I know my angle is the inverse tangent of x over r. So that's my theta. So I can, if I do tangent of theta, that's my x to r ratio. If I add complex numbers, you're going to add them as, add all your r's and all your x's. Don't use polar format. You're going to have to convert a polar format to this to be able to add numbers and subtract them as well. And if you add, and I'm just showing you here that R1 plus R2, and basically look at the triangle, you're just filling in that gap, and your R's, all your reals add up, all your X's add up, and then you'll have a new angle. Or if both of those numbers were at the same exact angle, the angle will be the same. Now, if you multiply, I'm going to do this using rectangular and polar for you. You got 5 minutes. I'm going to multiply Z1 times Z2. Remember, Z1 is a complex number, R1 plus JX, and Z2 is R2 plus JX. To multiply these out, you take R1 times R2 plus R1 times JX2 plus JX1 times R2 plus JX1 times JX2. And remember the J squared. Look at that last number right here. You have X1 times X2, and you have J times J. J times J is J squared, and we know J squared is a -1. So if you didn't have polar on this, you can do it the long way, and we're going to do an example. So we're going to multiply 2 plus J6 and 4 plus J12. And you're right, Felix. It's the soul of electrical engineering right here. Power systems engineering, complex numbers, and per unit is like, it's just the cat's meow. It's what makes you different. So if I'm going to multiply 2 plus J6 times 4 plus J12 the long way, using not using polar coordinates, I'm going to take 2 times 4 plus 2 times J12 plus J6 times 4 plus J6 times 12, J12, right? So I'm going to have this 2 times 4, 2 times J12, J6 times 4, J6 times J12. And I'm going to simplify. 2 times 4 is 8. 2 times J12 is a J24. J6 times 4 is J24. J squared times 6 times 12, 72. So J squared, remember, J squared is a -1. So I break that right over here down to -72. So that plus 72 becomes a -72. And then I add them all together. I add my 8, subtract 72, I get a negative. I'm going to get a negative number for my real, for my resistance. And I'm going to get a positive number for my reactance. So I'm at -64 plus J48. Now let's take a look. If I break that down into a phasor, that is 80 at an angle of a -36.87. Now, that 80 at a -36.87, if I do my R's and my X's, that's what the triangle looks like. It's got a negative resistance. You'll say, how the heck can you have a negative resistance? What is a negative resistance? How do I measure a negative resistance? You don't. You don't. But that 80 at a -38.6 is exactly the same as 80 at an angle of 143.13. Right? So I'm, instead of representing it at an angle of negative, I'm going to say it's a positive 143.13 just by taking 180 degrees minus the 36.87. Now, To check our math, we're going to do it via the polar method. So now I'm going to do this the short way. I separate each of these numbers into their polar coordinates. Remember, the polar method is to the phasors. The magnitude is r squared plus x squared square root at an angle of the inverse tangent of x over r. So I have 6.3246 at an angle of 71.565. And Z2 is 12.649 at an angle of 71.565. They both have the same angles. Convenient, but doesn't matter. Doesn't matter if they're the same or not. And now, when I do my multiplications, I multiply my magnitudes and add my angles. It's that simple. So I multiply 6.3246 by 12.649, and I add 71.565 together. And what is my number? 80 at 143.13. Now, if I compare that, I get my real and my reactive. 80 cosine of 143.13 is a minus 64. 80 sine of 143.13 is a plus 48. Now let's compare that with our other numbers. 80 at 143.13, minus 64 at 48. I get the same answer both ways. So now you know how to multiply the long way. If you don't have polar coordinates on here and you can't figure out how to do the inverse tangent manually, do it the long method. And you might see something like that on a test or exam or something like that, like a PE or whatnot. I can't remember if I ever had that, but you never know what's going to be on a PE. And then if you're dividing numbers, you do you basically take Z1 over Z2 and you subtract the angles. Now, I did not do the long way to calculate. Oh, yeah. Oh, James, we're going to answer that one. We did not do the long. I didn't do the long way, but I will. I'll put the equation up at some point. Okay, James Smith. I have an HP 35S. You have a 30. I'm not sure about a 33S. What you need, here's what you need on your calculator. I'm gonna put this up here like this. Let me do this. Let me I'm gonna let me focus this. Figure video and controls, and I'm gonna do a focus. Here we go. All right. So, James, and anybody who wants to buy a calculator or get a calculator, this is the function you're looking for. You see this I. I is the imaginary number. It just so happens HP is settled on I. We just settled on J. Remember? Okay? But look at underneath that. What does that say? Theta. So if I wanted to put three numbers in parallel, and let's say it was 5, okay, you know what? Let's say it's 5 at an angle of 45. And then I can do a STO for store. Where's STO? Inverse STO. 1. Store that in 1. And we'll say we do 5 at an angle of 45. And I'm going to do STO 2. And then I do 5 at an angle of 45. And I'm going to do STO 3. So now I have, if I do a recall 1, let me zero it out. Recall 2, I'll zero it out. I'll do recall 3. I've got all three numbers in there. Let's do the last. Well, I'm going to leave them at all at 5. Now, if for me to do, I can do, if I have conductors in parallel, right? How I would do it, I do it. I take the first 2 divided by the sum, and then take that. So there's a way to do that in a long way, but if you want to multiply 2 numbers, you take and you just do the multiplication. So if I have 5 at an angle of 45, 5 at an angle of 45, if I hit multiply, it does the multiplication. 25 at an angle of 90 for me. If I want to do a divide, I just do a divide and it'll do the division. So to make your math easy on those calculators, you basically, if you have that function of angle and theta and or I, you can convert things very easily from rectangular to polar, polar to rectangular. So, like for example, if I had, go back to me and my paper again, I'm going to have to redo the focus. So give me a second to focus this again so I don't blur you out. Focus. All right, so if I have my calculator and I have a, let's say that I have 5 plus J6. I do 5, I, 6. If I hit enter, at 7.81 at an angle of 50.19. So the calculator makes life a lot easier for you. Now, if I want to get that back over to back to rectangular, I believe I go function display, and there it is, ix xiy, and if I hit enter, there's my 5 plus I6. So I can convert on this calculator from 5 plus J6. I go, I'm doing the display, and then I go to theta, or R angle theta. I hit enter. It puts it back over to 7.81 at an angle of 50.19. So doing combining impedance values, whether they're 3 in parallel or 2 in parallel, in series, parallel series, the calculator can make it a lot easier to be able to multiply rectangular, and it does all of the stuff in the background for you. So you could put everything in as an R and an I, multiply, add, subtract, divide. The calculator will do it for you and show you the answer in an R and an I. And if you want to convert it, you just got to look. Every calculator is going to be different. I had a couple emails on how do I get that rectangular and polar on my calculator, and they gave me the number of the catalog, and I just went onto YouTube and Googled it and found it. So, piece of cake. All right, so we I think hopefully you got a little bit more insight today's session on picking your impedance values, some reference documents for transformer impedances, some rules of thumb to use. I talked to a buddy of mine, Dan Carnivali, up at our Experience Center. We're going to Ahmed, angle 80 at 143.13. 80 at 143.13 is not equal to 80 at a negative 36.87. So here's what I would do. Let's do this, Ahmed. We have 80 at an angle of 143.13. And we have 80 at an angle of minus 36.87. So 143.13 cosine. Cosine of 143.13 is equal to minus 0.8. Sine of 143.13 sine of 143.13 is equal to 0.6. Right? So 143.13 cosine is a minus 0.8. 143.13 sine is 0.6. 36.87 negative cosine is 0.8. Minus cosine of a minus 36.87 is equal to 36.87 cosine 0.8. 36.87 negative sine minus 36.87 is a minus 0.6. Right, let's take a look. Take a look at what I had. What did we have? We had 36.87 minus 36.87. Yeah, 80 times 143.13. That's a good catch, Ahmed. Take a look at this. So you have minus 36.87. 36.87 minus, enter. Let's do 180 plus. Excellent. Thanks, Felix. Yeah, so that's a good, that is good. Yeah, so let's go back to this. I'm gonna go back to this math again. 80 at 143.13. That's what that works out to be. And that's the angle way. I'm looking back and see if there's anything that I take a look at me and just taking a look at the math here. So you got 2 times 4 is 8. J6 times 4, J12. So all of that math looks good. That's a negative 1. So 872 minus 64 plus J48. So it is minus 64 plus J48. So we know that for a fact. Now let's do, and what I probably did was, so what's 48, 64 minus divide inverse tangent is minus 36.86 degrees. And really, that is, so, all right. Okay, so my Z1 and my Z2 is a minus 64 plus J48. Minus 64 plus J48. So minus 64, and then you have your J48. And that angle, this angle here is your 36 point, what was it? 36.87. So this angle is 180 minus 36.87, which is your 140, what is it? 143.13. So that's what we're drawing when we do our R's and X's, and that's, so this would be a minus 36.87 angle. So I can't call that theta minus 36.7 because of where it's at. Theta is, this angle is 36.87. It's not a minus 36.87. So Amjad, you're correct. that that is not 80 at an angle of minus 36.87. Because minus 36.87 would be here. That's what that would be. Because I know that I have, because I know that my R is a minus, my R is a minus 64 and my X is a positive 48. I know that angle is 36.87. But how I would represent it would be 180 minus 36.87, which is a 143.13. So you're right. 80 at an angle of negative 36.87 is not equal to 80 at an angle of 143. And what you're saying there is correct. So if I drew an angle of negative 36.87, that would be there, right? Which would be 360 minus 36.87, which is 360, 36.87 minus 323.13. Now that is what I call teamwork. I'm Jad Marmash. Where are you from, brother? Where are you out of? Where do you call home? I'm just curious. And I want to say thank you. Awesome. Okay. We did a good 2 hours and 16 minutes, and you all hung in there. I got 22 of you out there. Thanks for hanging in there. Don't forget to hit the subscribe. What I plan to do moving forward is I'm going to take this power distribution system and we're going to start building it out. I think I'm going to add a couple more panel boards. I'm going to add a motor. I'm going to add a few motors, maybe some loads. We might do a motor starting study. We can talk about power factor correction. I talked to Dan Carnevale up at our Experience Center. He is a power quality guru. We're going to try to figure out how to demonstrate Palestine. Sweet. We are international. I really appreciate you dialing in. Awesome. So we're going to plan on doing a lot of power systems engineering stuff, in addition to my NEC regular curriculum stuff. And I just talked to an engineer or a contracting firm today, and about doing some educational stuff with them. And the question comes up to me always: what's your schedule of topics for my Thursday live at 5s? And I don't have one. I'm going to try to be more diligent so that you guys and gals will be able to have a schedule of what I think I'm going to talk about. So I'm going to try to put that together. I don't know if I'll be successful because I don't even know what I'm going to talk about next week right now. So it's around Saturday morning. I sit down and I'm with whatever I'm doing out in the garage or around with my wife and whatnot. I'm sitting. I'll think about what's the topic for next week. So I will. I'll see if I can come up with some stuff. So James, thanks a lot for the feedback, brother. We had some. Thanks for all of your engagement. We got Felix out there. You guys are awesome, and I really appreciate everybody dialing in. Brian Rock dialing in, and Gustavo dialing in. Felix Sandoval, Don Ganier, Gustavo Chavez. All of you guys are awesome, and we have a person from Palestine. We had Nihad El Sharif, who was over in Egypt. So we're international, and we got Felix Sandoval, who's down in Colombia. So we're kicking butt, taking names. Thank you for dialing in. Thanks for what you do for electrical safety and for the electrical industry. Until next time, I'm going to be signing off. So we'll see what happens. We'll see what we can come up with for next Thursday. And maybe something in between. You never know. So I feel like talking about arc flash. I don't know why. I feel like talking about incident energy. Maybe we'll. Oh, we haven't picked the circuit breakers for this installation. In fact, on my one-line diagram, I didn't even put any circuit breakers in the one-line diagram. I go straight from conductors. I didn't put any circuit breakers or fuses. So maybe what we'll do next week is we will pick our overcurrent devices, and we'll pick some breakers and fuses, and we'll do probably we'll take a nice little brief look at selective coordination. Sound good? All right, guys, gals. Thanks for joining in. Appreciate it. Remember to subscribe, hit the thumbs up, hit the bell so that whenever I go live, you know about it. Sorab Alma-Jose, where are you from? Sohrab. I probably butchered your name. Sorab Alma-Jose. Let me know where you're from. Mather Abbasi. Awesome. Good night, Mather. Appreciate you dialing in, brother. I'm curious where Sorab is from. I know there's a little bit of the delay, so type it in. I'd love to hear you. You do not have to change anything. It's just perfect. Awesome, Felix. I really appreciate the feedback. I really appreciate it. You know, I do a couple of these on fly. Oh, Haile Selassie. Awesome. Kahali, how you doing, buddy? Man, I haven't talked to you in a long time. I hope you're doing well, Kahali. It's really good to see your name. Really good to see you out there. I appreciate you dialing in. I hope you and your baby, your family are doing great. I know you just had a new baby when you left Eden, so I hope you are doing well. I know you are. I know you are. You'll succeed at whatever you do. So really good to see you and to hear from you. I have to tell Bobby Joe that you were on a program tonight. So thanks for dialing in, everybody. Gustavo, crew, Kahali, Michael, Riza, thank you for joining in. Have a good evening, and let's hit it tomorrow. And hopefully you stay warm and dry and COVID free. So thanks for what you do. Stay safe, stay healthy, and we will see you next time. Signing off. Bye.